Hello everyone. Today in this video, I'm going to talk about a problem related to gravitational force where we have to use Newton's law of gravitation. If you read the question carefully, it says there are two solid spheres of radius r and they are made out of the same material. The two objects, the two spheres are in contact with one another. When they're in contact, each of these spheres, they will experience a gravitational force of magnitude F. Okay. Now, there are two other solid spheres, but with different radii. Actually, it's twice the radius of the original one. And now they are made out of the same material and they are also in contact. If this is the case, what is the magnitude of the gravitational force acting between these two larger spheres? So that's what we need to find out in this problem. So let me show you case one. We have the smaller solid spheres in touch with one another. Okay, that's the center. We don't know the mass. Let's call M and M. Now the masses are the same because they have the same size and they are made out of the same material, meaning that they have the same density. So that's why I'm saying that they have the same mass M. Now the radii of each one is R. So then the center to center distance would be 2 times R, right? Now, why did I select center to center distance? Because since these are perfect spheres with the same density, uniform density, we can collapse the mass of each of these spheres to their center. Okay, so here I'm going to assume that the entire mass is collapsed to the center. Okay, and now the force, the attractive force or the gravitational force between these two masses is F. That's what is stated in the first part of this question, and that's what I call case one. Now let's look at case two. Case two, we have two large spheres, each one having twice the radius of the original one, and they are made out of the same material like the previous one, and they are also in touch with one another. So like this. This is case two. Okay. So we don't know the mass. So let me call that M prime. And then this radius is 2 times R. And this radius is also 2 times R. Remember, they are not drawn to scale. Okay. It's just a sketch. Just like the previous one, the entire mass can be collapsed to the center of each of the spheres. So I have M prime and M prime. And then this separation is, you can see, 2R plus 2R, that is 4 times R. And then what is the new gravitational force between the two objects? That's what we need to find out in terms of F. So let's call this F prime. We don't know F prime. So the objective of this problem is to find what is this F prime. That's the objective. Okay, so I'm going to use two important equations in order to solve this. The first one, Newton's law of gravitation for point masses. So if there are 2 point masses, M1 and M2, placed with a separation of R, then the magnitude of the attractive force or the gravitational force between the two objects, F, can be written in terms of big G, that is the universal gravitational constant, times M1 times M2, those are the two masses, divided by the separation between the 2 point masses, actually separation squared. Okay, so that's the magnitude of the gravitational force. Then another equation that I'm going to use is the density equation, because you can see all these spheres are made out of the same material, so they have the same density. And in one case, I need the mass. So mass and density, there's an equation that connects mass and density. I'm going to use that. So that's the simple equation: mass is equal to density times volume. Okay. So let's look at the first case. And let's try to see whether we can apply mass equals density times volume. So just looking at case one, M can be written as rho. Now, what is rho? That's the density. Okay, now it's a very common symbol for density, rho, so I'm going to use that. Mass for the first case is equal to density times the volume of the sphere. So volume of a sphere is 4 over 3 pi radius cubed. Okay, so I'm going to write 4 over 3 pi, and the radius is big R, so big R cubed. Okay, now for case 2, let me call that equation 1. And for case 2, similar to equation 1, I can write M prime is equal to the same density, it's the same material, times it's the volume of a sphere, but the radius is different. So 4 over 3 pi, instead of R, you can see it's 2R cubed. And that's my second equation. Now, using these two equations, I can find M prime in terms of M, the mass of one of those original spheres. So I'm going to use some algebra here. 2 over 1, as you can see, will give me M prime over M. You can see the density, rho and rho cancels out. Okay. 4 over 3 and 4 over 3 will cancel out. Pi and pi will cancel out. And then I'm going to get 2r cubed, the cube of the entire thing, divided by r cubed. Okay, now this is simple algebra. You can see 2 to the power 3 is 8. And then I have r cubed in the numerator and r cubed in the denominator. So they will cancel out and I'll just get 8. Okay, so M prime, the mass of the larger sphere M prime, is 8 times the mass of those smaller spheres. So that's an important relationship that we are going to use in order to find this F prime, the new force acting on the larger masses. Okay, so now I'm going to utilize Newton's law for gravitation. So using that, we can have F is equal to G. I'm looking at case number 1, G, M times M. I'm going to write M squared divided by the separation is 2R squared. So I'll write 2R squared. And then again, you need algebra here. We can simplify this further as G M squared divided by 4r squared. So I can write this as equation number 3. Okay. And then I'll go for case number 2 and I'll write down F prime in terms of Newton's law for gravitation. F prime is equal to, again, big G. This time the mass is not M, but it's M prime. So M prime squared divided by the separation squared. The separation is actually 4r. So we have to take the square of that 4r squared. And then at this point, you can go ahead and substitute for M prime. So then we can further simplify. G m prime is 8m squared divided by 4r, the entire thing squared. Simplify this further. We have, like, in terms of numbers, 64 over, so there's 8 times 8 is 64, divided by, this would be 16. Okay, and then we have g m squared over r squared. You can further simplify this as, like, there are 416 in 64. So you can have 4gm squared over r squared. So let me call this equation number 4. So now we can use equation number 4 and equation number 3 to figure out f prime in terms of f. Okay, so that's my plan. Okay, so I wrote down equation number 3 and 4 again on a new slide. So now let's try to use algebra and simplify this for f prime. So what I'm going to do, I'm going to divide 4 by 3 like that, and then you'll have f prime over f, and then f prime would be 4g m squared over r squared, and in the denominator I'll have g m squared over 4r squared. Okay, so you can see g m squared over r squared is common, so they will cancel out like this, right? And then you have a 4 in the denominator, like it's 1/4. If you look at the math, it's like this: 4 divided by 1/4, and that 1/4, the 4 goes to the numerator, so it becomes 4 times 4, basically like 16. Okay, so then we have f prime over f is equal to 16. That means f prime, the new force, is 16 times the original force. So this is how you get the answer to that question. Okay, so this is the question again. When you double the size, when you double the radii of uh, two masses made out of the same material, what is the new force acting between the two masses in terms of the old force? So it's 16 times the old force. So this is how you do the question. And if you have any questions, any concerns, points to clarify, please, put it as a comment, and I'll go ahead and reply to your questions. Thank you, and have a great day.